I would like to welcome you all in the lecture series of power electronics. In this session, I am discussing single phase full wave controllers with resistive load. How does single phase full wave controller with the resistive load operate? First of all, I would like to introduce the circuit diagram of single phase full wave controller with the RL load. Here, Vs is nothing but the input voltage. It will have positive half cycle and a negative half cycle. I can represent like this. We have positive half cycle. This is negative half cycle. Now the input is supplied to the resistive load through the two thyristors which are connected anti-parallel. So we have T1 and T2. Both are connected anti-parallel, or we call it as inverse parallel. So we can see like a anti-parallel connection of two thyristors, that is become as an interface between source and the load. Now we'll discuss how does it work. Now I'll be showing you the operation. Okay. First of all, during the positive half cycle, the input power flow is controlled by varying the delay angle of thyristor T1. Let me make it clear. During positive half cycle. So positive half cycle means positive comes over here, negative comes over here. So during positive half cycle, what is going to happen? The thyristor T1 will be turned on at a delay angle of alpha, So the power flow will be taken place from the source to the load. So you can mark like this. This is actually happening when during the positive half cycle. Okay, positive half cycle. Make sure that your device is activated at a firing angle of alpha. Now, what is the next condition? You already know that AC waveform, it has positive half cycle as well as negative half cycle. Now, we'll see what will happen during negative half cycle. First of all, I will draw how it works during negative half cycle. Negative half cycle means negative comes over here, positive comes over here. Correct? So here, during the negative half cycle, what exactly happening is, during negative half cycle, exactly see, the thyristor T2. See, thyristor T2, that will be activated at an angle of pi plus alpha. See, the thyristor T2 will be turned on at a delay angle of pi plus alpha. Therefore, power flow will be taken from source to the load. So here, thyristor T1 will not be conducted, where thyristor T2 will be conducted during negative half cycle, because the negative comes over here, right? Negative comes over here, correct? That means cathode is negative with respect to anode. So conduction will be done during negative half cycle. So the power flow will be from in this fashion. T2 will be conducted. You can mark like in this fashion. Okay, done. This is actually happening during negative half cycle. So this is the working of single phase full wave controller with the R load. R load. So now I'll be introducing one more thing. This is regarding R load. Okay. What is the speciality of R load? Here, voltage and current are in phase. That means delay angle will be 0. There is no changes in delay angle. Okay. So delay angle will be 0 only. So now I'll be showing you the waveform so that you will be having the better understanding. So waveforms are very clearly explaining. So we have the supply voltage Vs and the peak value is called Vm. It has positive peak and negative peak. Now during the positive half cycle, the device T1 is getting conducted at a firing angle of alpha, at a delay angle of alpha. T1 will be activated. Here it is very clear that current follows voltage, or voltage follows current, because both are in phase. Okay, it will be conducting up to whenever the positive half cycle ends. Positive half cycle ends at pi. Now, during the next half cycle, during the negative half cycle, what is going to happen? The T2, see, look at this. During positive half cycle, T1 is activated. During negative half cycle, the gate pulse of T2, we are going to provide the gate pulse at T2 at a delay angle of pi plus alpha. Here, the conduction will be taken place. Okay, delay angle. So what is the delay angle? Pi plus alpha. So both the current and voltage are in same phase because we are using the resistive load. Here VG1 and VG2 is nothing but we are providing the suitable gating pulse. VG1, that is we are going to provide at a delay angle of alpha at T1. VG2 is nothing but gate voltage at T2. So the what's a like delay angle you are going to provide pi plus alpha. Correct. So the shape of the output, that is also AC only, right? So positive half cycle, negative half cycle, but it's a controlled AC. So we have fixed AC. Okay, fixed AC. What is the outcome? Outcome is variable, variable AC. Correct. So we are controlling at a delay angle of alpha and pi plus alpha. This is what exactly happening. Now we'll go through the mathematical expression, which will be helpful for the numerical example and the design segment. So this is very important. You should know the basics. I'll be showing you the MATLAB simulation thereafter. First of all, you can understand the theory. Thereby, the simulation will be pretty easier for you. Now we are going to calculate you what is the average output, sorry, RMS output voltage. What could be the RMS output voltage? The question will be like this: derive RMS output voltage. What is the average output voltage of single phase full wave converter or single phase full wave controller, single phase full controller with R load? First of all, you can write like the supply voltage Vs equal to Vm sin omega t. So I'll be writing Vs equal to Vm sin omega t. What is Vm? Vm is nothing but maximum voltage. So maximum voltage can be written as root 2 into RMS voltage sin omega t. Same thing I have written here. Correct. Okay. Okay, now what you can do is can apply the output voltage. V naught is equal to average output, RMS output voltage you are supposed to calculate. Then square root of 2 by 2 pi alpha to pi 2 V square sin square omega d omega t. Here both are same only. See, square root of x, that is equal to x to the power 1 by 2. So same manner I have written here. Correct. Now by elaborating, a sine square omega t, you should understand that sine square omega t direct integration is not possible. So you convert cos 2 omega t divided by 2. Same thing I have written here. So 2 will come denominator, so it becomes like a 4 pi. Now 2v square, no, 2 into 2 means a 4v square. Alpha to pi you can give. So ultimately, the RMS output voltage, V naught RMS can be written as Vs into 1 by pi, pi minus alpha plus sine 2 alpha divided by 2. So the same application application is light dimmer. Light dimmer. Okay. Light dimmer. You can use the light dimmer. Correct. So this is regarding single phase full wave controller, single phase full wave controller with the pure resistive load. You take care about like the load, what kind of load you are going to use. So resistive load means you can like give a best example as a lighting load, normal type of light load, like lamp load. You can call it as a lamp load. Okay. Now the problem is in this particular circuit, which you can observe, there is no like isolation between the thyristors and the firing circuit. Where is the firing circuit? Can you show me? Here we are going to provide the VG1, right? Here we are going to provide VG2. These are called a firing circuit, like this, firing circuit. Okay, firing circuit. Okay, that will operate with a very tiny voltage, maybe less than 5 volt. But the thyristor that will operate more than 100 kilovolt. It can operate with more than 100 kilovolt. So the problem is there is no isolation between the signal, signal level voltage and power level voltage, power level and signal level. There is no isolation. So what to do? So if we are not providing an isolation, our gate circuit is getting spoiled because of heavy voltage. To overcome that, what you are going to do is you will be doing one new design called the common gate technique. Common gate. You are going to provide the common gate like this. See, common cathode, not common gate, common cathode. See, look at this. Cathode of, this is your cathode of thyristor 1. And this is the cathode of thyristor 2. So here we are going to provide the common cathode, such a way that you are protecting your like the gating circuit from gating circuit against the high power level circuit, high power, right? So common cathode is provided. Also for the bypassing, what you are going to do is two power diode you are going to use. We have power diode D1 and power diode D2 for the better bypassing. Here, how does it work? During the positive half cycle, of course, supply will be like this. So here, what exactly happening? So diode D2, this will not conduct, right? So here, thyristor T1 is getting conducted. It will be conducting at a delay angle of alpha. Now what is going to happen? The bypassing will be taken place. See, diode D1 bypassing. You can check the path which I am going to draw. It will be pretty convenient. So it will come back to the negative side, right? This is actually happening during positive half cycle. So that there will be better isolation at the point of view, especially for the gating circuits. Correct. Your circuit is getting protected. Now I'll be telling you how does it work during the negative half cycle. So during negative half cycle, the thing is polarity is getting reversed, negative, positive. Here the thing is diode D2. There is a conduction of diode D2. See, of course, the thyristor T2 will be conducting at an angle of delay angle of pi plus alpha. Like this conduction will be done. So this is what exactly happening during negative half cycle. Thus here there is a bypassing. During positive half cycle, exactly what is going to happen? T1 and D1 is getting conducted. During negative half cycle, T2 and D2 will be conducted. That is what exactly happening here. The main problem is we require high power rated diode, especially MUR1560, one of the diode commonly used in practical application. MUR1560. It's a high power rated diode. It's too expensive. Okay. Expensive diodes are required. As many components are included in the circuit at that particular indexed manner, the efficiency will come down. As the number of components are high, the efficiency will come down. So more conduction losses will be taken place. That will hamper the overall efficiency of the system because as many components you are included, at that instant, the overall efficiency will be reduced. That's a major problem. To overcome that, we have one more technique we can use see, we can use modified full wave converter in this fashion. Look at this. So we have like a diode. Diodes are just connected just like a bridge format. D1, the D2, D3, D4. So here these are our power devices. Power devices can be like either thyristors or transistors. Correct? Yeah. So we will be making a better connection. So we'll be making a better connection such a way that the overburden will be reduced and it will give more safety. Okay, so this is another circuit such a way that we can improve the overall efficiency. Okay, it is applicable for both the transistors and thyristors, correct? So it will give a better isolation between the power circuit and control circuit, so the circuit will be 100% safe. In this session, I discussed about single phase a full wave controller, or we can call it as a single phase AC voltage controller, single phase AC voltage controller with a pure resistive load. One of the best application is your light dimmer circuit. Let me know if you have any queries regarding this. So I have already taken the videos of light dimmer that I'm going to upload in the coming session. Apart from that, we can have a simulation so that you'll be having the better understanding. So may I know if you have any clarification? I'm happy to answer back from my knowledge. Thank you very much for watching this video. Happy learning. Have a great day. Thank you again.